Swayam Prabha. Digital India. Educated India.
The topic that was given to me is projected here. Traffic engineering and planning was what is given to me. I corrected it little bit to call it as traffic engineering and transport planning. Okay. Why is it so? Why did I correct it? No. Okay. You are not used to answering. So let's move on. So what is traffic engineering is they will edit whatever they don't want from here. So what is traffic engineering as per your understanding? I need answers. There is no way otherwise I can teach. Traffic engineer. Okay. But that what is that life cycle include? Different tasks. Before construction there is one more stage. Yes, planning. Then construction. Okay, good. You looked at the slides, I guess. Okay. Okay. Let's come back. So, stop. So, this is what I got when I searched in the Google pictures, Google images, what is traffic engineering. So, I see intersections, interchanges, vehicles moving, what else you see? Then there is one which is having lot of text saying traffic models, traffic control, traffic monitoring, intelligent transportation systems. So all these are covered by what he said is what I believe. So let me show you the simplest definition I saw in a website. It is a very simple website. It says traffic engineering is a branch of civil engineering that uses engineering techniques to achieve safe and efficient movement of people and goods. Very simple, right? And it conveys what traffic engineering is all about. It's all about moving people and goods from one place to another. The major conditions that you add is safe, efficient and economic movement. So, this is what the traffic engineering is. And why do we do this? There are mainly three problems which we talk about. One is congestion, the other is safety, the third is pollution or emissions. So, when you say we have to design this system, we are talking about how do we address these problems. So, design the things such that these problems are minimized. And what is the problem here? When you are trying to minimize some of these, or when you look at these objectives, let me go to the next slide. So, the basic objectives you will see in any textbook, anywhere you read is like safe, efficient and economic movement of people and goods. So, what is the problem here? I have a problem in this three objectives that we are talking about. Okay. When you talk about safe, how do we make a traffic system safe? So, usually you talk about reducing speeds, right? That's how you make it more safe. But then if you want to make it more efficient, what should you do? You have to make the move as fast as possible, right? So, we are seeing some conflicting objectives in the whole process. That's the difficulty. So, we always look for the optimum way of handling these problems. How do we make them move fast enough and safe enough? But it's again, you can't say that average is good enough. We want the minimum accident. So, we cannot say 50% is good enough for me. So, that's one of the major challenges you will face when you are trying to do this. And what are all the components that we are talking about? There are mainly three components. One is what you already discussed, the infrastructure, the roadway, the railway, the airport and all those things. The second is the moving objects there, the vehicles, the train, airplane. So, that's where I am going to concentrate maximum in this discussion because the infrastructure is something which you already have listened to in two different talks. And the third component, which is the most complex one, is the human component in it. There is always a driver, there is always a pedestrian who is involved in the system. And that component is not under your control. In the sense, it's not easy to model it into your equations or anything. because human behavior is very complex, right? So the challenge in terms of modeling this traffic movement, once the infrastructure is there, the most complex part is how do we characterize the driver behavior. For example, different people will behave differently for the same situation, right? So, how many of you have driving license? We haven't reached that. Two-wheeler at least? Two-wheeler at least you have, right? So, you and your friend drives, you don't behave the same way when you have the same situation in front of you. You yourself may not behave the same way for the same situation at different time periods. So, if you have to kind of capture this behavior into your models, it becomes highly complex, right? So, these three components, each of those, how do we handle? For the other part, vehicles, if you take, even if you restrict to the roadway movement, there are bullock carts, there are two-wheelers, there are auto rickshaws, up to trucks. How do we kind of incorporate all those different types of vehicles into the design, right, for management? How will we do that? So, and what you need is finally a system which is as uniform as possible, right? You don't want different, or you don't see different roadway for two-wheelers and different roadways for trucks, right? That's correct. So, another challenge which you are going to see is you have varied components, in the sense you have different types of vehicles, different types of users, and you want to provide roadways and the system which is very uniform. So, how do we handle these challenging problems is one of the problems we will talk about. So, before getting into how do we do that, what are the classifications of these systems? So, you classify the system based on what technology you use, what service you provide, who operates it, what are all the medium. So, each of this, do you understand when I say what mode, for example, is it rail versus air versus roadway, for example. That's one of the ways. So, by mode you can see these are all the different ways in which one can commute from one place to the other. Simplest being walking, running, whatever you want to. Then there are different types of vehicles, you can, roadway vehicles, then there are boats, ships, aircrafts, all those. In some way, if you group this, you can say there are land transportation, air transportation and water transportation. Each of those have a bunch of different types of vehicles. A different way of looking at the classification is urban versus intercity travel, freight versus passenger movement. So each of these has uniquely different ways of handling. So these are all different ways of classifying the system. Now coming to the formal definition of traffic engineering, what we saw was a very simple, crude way of starting, saying that move people and goods from one place to another. Here is the definition you will see in any textbook, for example, and this is restricting it to the roadways alone. It says it's planning, design, operation and management. What he repeated is what the formal definition is. So these are the stages you will go through when you have to do a complete design or complete system development for transportation. And each of these terms, planning, design, operations, management, I will explain in one slide. Each of this is a separate course eventually. You have 2 undergrad level transportation courses which will cover all these in a very brief way. Then there are separate courses for each of these which will cover the complete details. So what's planning, what's design, what is operations and what's management? Design is what you heard little bit already from the other lectures, I believe, which talked about how do you design the permit, for example. If there is a traffic norm, how do you design the roadway? But even before designing, you have to plan the system. So why is it important? One characteristic of this transportation is you don't usually you don't make a trip just for the sake of it. You don't go for a drive. Okay, very rarely, maybe 1% you will do just for the thrill of riding a bike or something you will go. But most of the time you are traveling for some other purpose. Either you are going to your class or you are going to a movie, you are going to visit someone. So there is an end reason for you to make the trip. So that's what is meant by the derived there is a term called it's a derived demand. So the trip you make is related to some other activities. Most of the time it will be socio-economic related things. So the land use plays a major role in what trips happen. Correct? If it's a recreational area, the trips are mostly to visit the place. If it's a residential area, the trips are usually people want to go to their workplace or they want to go to their colleges. If it's a shopping area, people go for shopping, obviously. So each of these trips is related to the land use of that area. So the planning part kind of links the land use to the trips that you make. So when you say you want to plan something or when you want to plan a transportation system, you start with the land use of the area. So if let's say somebody says that they want to move the capital from Chennai to some other city. So you will have to design the entire transportation system there. So you will start with looking at different zones in that area. What is the land use of each of that area? Then you start planning. So how do we do that? And usually this planning and design is done for a period of around 20 years, 15 to 20 years. So the planning part has 4 major steps. I am not going to get into the details. But they are called trip generation, trip distribution, model split and route choice. So what we are saying is first you want to find out how many trips are generated from each place or how many trips are attracted to each place in the first stage. Second stage what you are doing is you are trying to say from this zone to this zone this many trips happen. That's the trip distribution step. Then you are looking at how many of those trips are done in different modes, two-wheelers, how many cars, how many public transport, how many. And the last part is which route each of these trips happen. So at the end of this 4th stage, you know from each zone to each zone how many trips happen by each mode through which route. You understand? So at the end of this, you know that this route, this many two-wheelers and this many cars have to go. Then you get into the design where you will use this information to design what type of roadway you need, how much thickness you should give, what material you should use and all those. So that's the next stage which is the design. So there you are looking at how do I design this system or the roadway. So you will be getting into what I said as the hard side of it. Basically you are looking at how do I do the characterization of the material, how do I design the thickness, how do I check the stress and strain so that's generated, whether it is safe, whether it will crack, all those information you need. So this is more of the structural design of the roadway. That's one part. You would have heard some lectures on structural design of buildings. Similar to that, we are talking about structural design of roadways. Once that part is done, the other part is the geometric design where you are looking at how do I design the curves, how do I make sure that the vehicles are not thrown out when you are negotiating a curve, or how do I make sure that a vehicle don't slip back when they are climbing an uphill. So you have to make sure it's done correctly. So that's the geometric design part of it. As I said, each of this is a separate course. Geometric design of highways is one separate course and offered from the transportation division. So this is the second stage. So it was planning, design. Third is what is called as the operations. How do we control or manage the vehicular movement on a roadway? So there is no way you can communicate with the driver. As an engineer, you don't communicate with the driver by calling, hey, you cannot go this way. So you need some kind of media to communicate with your drivers. That's what these operations mainly is. It's mostly about signs, markings and signals. You would have seen all of these. So markings are on the roadway, signboard sit in the roadside and then signal sits there either in the roadside or across the road. So these 3 kind of tell you how you should behave in a roadway. So the operations usually is how do you design the signals, how do you make sure the signs are correctly placed and correctly conveying the information that it should do. So it's again separate course which is on signal design, signal analysis and all those things. The last part is mostly on the management. Once you have this, how do we handle the traffic still, in terms of, mostly you see this being done in India by the traffic police. Right? Suddenly the traffic police decides that this road has to be a one way because there is problem. Ideally, it should be done by traffic engineers, but here mostly the police people do that. But these are different ways in which one can manage the traffic once you have the roadway done, signals in place and all. Okay. So, having said these 4 steps, planning, design, operations and management, we will mostly concentrate on the operations and management part. That's what the soft traffic side of it. So, you have the planning done, signal design, roadway design done, and how do we make sure they are moving efficiently, right? That's what this is. So, one major part is you have to model the traffic. You have to you have seen, modeling of different things. For example, rocket, if you have to design, first you start with equations that will decide how it's going to move, how its trajectory is going to be, all those. Similar way, you have to have models which will characterize how this traffic is moving. It's in one way to find out how this traffic is going to behave at different time and different locations. That's what the modeling is trying to do. And for doing that, you have to collect a lot of information. Traffic studies will come up, and then the modeling part, which can be statistical modeling, it can be mathematical modeling, it can be just data-driven models, empirical models, all those. But some way you want to model. And the other question is, how do we model this system? There are vehicles, then there is all the vehicles moving on the roadway, then there is the city level network. So, which one do you model? That's where these terminologies come. There are microscopic models, which are individual vehicles, how do they move. The macroscopic models kind of come out with equations or ways in which you will know how the traffic as a whole is moving. Then there is network level. In a city level, if you want to model, you don't do even at a very road stretch how the traffic is moving. So, how do we do it at the network level? Each is challenging in its own way, because for example, if you take microscopic level, how one vehicle will follow its leader. It's challenging because it heavily depends on the human behavior, the driver who is sitting in the vehicle. So, how do we include all these into the modeling and have some reasonably good models is what comes under the discussion in traffic flow modeling. And this is something which is more recent. By recent, I mean in 70s it started, but still the other things are 30s, so 1930s, this is in 1970s, what's called as intelligent transportation systems. Many of you would have heard this term, I hope. So, what we are talking about is, so far whatever we talked was done in a very traditional way. You collect some data by going there, manually collecting, analyze it, come out with something. With latest technologies in terms of sensors, in terms of communication, in terms of analysis, there are new ways in which you can handle these problems, whether it's operations or whether it's management. So, that's what the intelligent transportation system is. So, this is again a textbook definition. It says that any advanced communications, control, electronics, computer related technologies being used in traffic. That's what the intelligent transportation system is. So, I will just quickly discuss a little bit on ITS, because the latest trends in terms of connected vehicles, automated vehicles, all those comes from this starting point of ITS. So, ITS, there are many examples. Your Google driver assistance is a classic example of a ITS technology. What do you get there when you are using a Google Maps? When you start your drive, usually you do, right? Whoever is driving, keep the Google map ready there. This is my origin, this is my destination, which route I should take or how much time it will take, right? How is Google coming out with that information? Any thoughts? It's okay, they are recording, but that's fine, you can talk. No thought? How is Google coming out with this information that, this much time it will take for you to reach this point? Satellite. How will satellite get that information? Okay, it's all coming from your cell phones. Okay, if you use your Google Maps, there will be some fine print somewhere there that your data will be used. and many of you are using it, so they know roughly what is the traffic situation in that road at that time. And they have their own analytics in the background to calculate and tell you, okay, this is roughly the time it will take, and this may be the best route to take at this point. Right, so there are many examples that you have seen already. For example, route guidance, Google is one example. Pictures like or message boards like this, which will tell you which route to take, how much time it will take. Or bus arrival prediction, area traffic control, signals being advanced. The current signals which you see, for example, have static time. It always have this much time of green, this much time of yellow, and this much time of red. And there are times in which you go there, you are in a red, the other side is not having any vehicle, but they have a green. Right? It's kind of frustrating. So, how do you make it advanced? If there is a way to collect the information from each of those legs and process it and tell, okay, this leg there is no vehicle, so don't give any green. This leg has vehicles waiting, give green. So if it can happen in real time, that's an example of ITS. So what did it do? It collected the real time data, processed it, found out what is the best way to handle it, and then changed the signal accordingly. That's a classic example of a ITS application, right? So if you look at any ITS implementation, the four major components is sensing the data, communicating the information, processing the information, and then deciding what to do. Or actuators which will kind of give back this information to you. So this needs lot of sensors, obviously, right? The sensors can be at different places. It can be in the vehicles, it can be in the roadway, it can be in the human beings. So, and with the advancements that's happening, there are enough sensors that gets deployed into your vehicles. For definitely there. Within you, for example, your cell phone is a very good sensor. It gives lot of information. Then roadside there can be enough sensors. So slowly we are also reaching there. Many other countries already have sensors deployed everywhere. And all these sensors are communicating with each other, which leads to what are called as this V2X communication, Internet of Things. You must be hearing all these terms, right? So every device or every component of the system is now giving information to each other. They can process this information and know how the traffic is moving. So these are different ways in which you can have sensors in a vehicle or roadside. So as I said, this leads to what are called as Internet of Things. Communication can be vehicle to vehicle, V2V, V2I, V2P. So in general, V2X, vehicle to anything. Communication can happen. And this is the basic component or basic concept from which these connected vehicles, this is one of the hot topic you will hear, connected vehicles. That happens because of all this information, and yes, once you have lot of sensors, lot of data. So you have to get into data analytics. So a lot of information can be processed. If you ask me, I am still somebody who believes, back to mathematical modeling is best. But I am getting proven to be wrong. There are places where a lot of data actually gives you enough information than a mathematical equation can capture. So there are cases where a lot of data is available, it can make sense. So there are, at least Google and all are using big data analytics. They have a lot of information with them, they have just processed. They don't try to understand the physics of the problem. They just look at the data and the behavior and the pattern so that they will be able to give you information. So as I said, this leads to what are called as the connected vehicles and automated vehicles. You must have read about this Google's driverless cars and all those things. There are enough countries where they are already running in the roads. Will it come to India? It needs time, needs lot of time, because we have a very unique way of driving. But in many other countries, we have these kinds of vehicles. So all these, the starting point is having enough sensors and enough communication happening. That was kind of quickly giving you an overview of various things that can come up in this traffic engineering and planning side. Having said that, I thought I will just tell you what's the Indian context to all this. So some of you may be thinking, why are we talking about connected vehicles and all when we are still building infrastructure? It can happen in parallel also. So this is one way of looking at it. You again would have heard about the smart city initiatives of the current government, previous term itself. So mobility is one of the verticals under the smart city initiatives, and that's what I have highlighted. They have given some examples: smart parking and intelligent traffic management, integrated multi-modal integration and things like that. But it's not that these are all the only things. They are interested in anything where you can use technology to make the traffic move better. So that's where some of these things can make sense. These are some of the details I collected from that website where they talk about what mobility features they are interested in. Let's not worry about it. But what I am trying to say is, under the smart city initiative, there is a lot of interest in terms of having such developments to be done. And yes, I have to do some PR work also to excite you. So these are some of the activities that are happening in our lab related to this ITS or traffic operations management also. So I will just briefly show you some of the examples just to show what your seniors have done. Many of the work which I am showing are done by undergrad students, either as part of the curriculum, mostly they were interested, so they just start working on it. So I have put mainly the activities are, we have developed a laboratory which is, I will show you some pictures, and we have a test bed, live test bed from where we are getting data. Then we have developed lot of sensors which work for our traffic conditions. Then some of the solutions we have developed and implemented. So as I said, one of the tasks I have divided into 4 headings. One is the lab development and the test bed, sensors, then data analysis and the solutions that we develop. This is the picture of our lab. Any of you can come and see the lab when if you are interested, we will make sure. So before I get into the details, why do we have to do this, right? I don't think I have to explain much. You know that our traffic is completely different from what you have seen elsewhere. And all the models, all the solutions that are developed are actually for the traffic which is lane based and homogeneous. By lane based, I mean them in one lane you expect only one vehicle. They move one after the other. They don't move parallelly within the lane, which we happily do. We don't believe in this, follow the leader behavior. We will occupy any space available. So it's in one way interesting. We are using the whole available space. We don't want to waste anything. But the problem is, modeling it becomes extremely difficult because you don't know how the vehicle is going to behave, right? Any gap you see, a two-wheeler fellow can move in whatever way. So how do we handle that? So any solution that's already available we can't use. We have to kind of redo the whole thing to meet this requirement of lane less movement. The other is heterogeneity. We have all types of vehicles. There are some 16 different types of vehicles that can be running on our roadways. So the typical US road, if you look, you have cars, you have trucks, that's all. Very small percentage of truck, maximum number of cars. So it's again very simple way of handling. So as I listed, heterogeneity is one challenge, lane discipline is another. These two together gives you enough uncertainties, randomness. So any model which you develop should actually be handling this randomness than the actual behavior. So your thing should be able to take into account the stochasticity in the model. So this you don't need, you know what lane discipline is. So why I said that is, many of you otherwise may wonder, why should you do this? This is already done in other countries, right? Most of these solutions or most of these things already is happening. Why do we have to? Because we have a unique way of handling. So as I said, we have a lab and a test bed. Lab is just a place where we are receiving all the data. The test bed is the interesting part. So we have a 15-kilometer corridor around IIT, SP Road, IT corridor. You may not be knowing, at least some of the Chennaites will know. So it's all the roads outside which are surrounding the IIT campus. The IIT is actually somewhere here. So, and we have kept enough sensors in those roadways. There are some, I have the details. So this is the first time an academic institution did that. Actually, even non-academic institution places, but they don't have it. So we have real-time data coming from field, we are processing it, we are having algorithms running, solutions being given back to the users. So the complete cycle we have implemented in this small corridor. What are all the sensors? We have around 300 MTC buses with GPS sitting and sending the data to our lab every 5 seconds or 10 seconds. We have around 32 video cameras relaying their feed to our lab. So then we have message boards which we have installed in the field which gives information back to the users. And there are other several sensors which I have enlisted. All of them are sitting in the field and sending us data. And many of the students were involved in developing sensors. So this is not purely a civil engineer's work alone. We collaborate with electrical engineers, mechanical engineers, engineering design. I have a slide showing all the collaborators. So we work, so I usually joke about this. If some of you may be, feeling very bad that you wanted to be an electrical engineer or computer science engineer and you ended up in civil, these are ways in which there is no fixed territories these days. It's all interdisciplinary. Nobody stops you from working in any of the topics you want. So this is one of the areas in which a lot of my students work with electrical engineering faculty, developing sensors. We have developed at least 4 different sensors which are working and giving information in a much better way than any of the available sensors. Details I don't have time, so I am not getting into. So obviously we have a good database, lot of data that's coming from all these sensors. And communication, we are using various technology, GPRS, wireless data transmission, regular wired connection, 2G, 3G modems, etc., etc. Lot of modeling that happens, which again I can't get into the details, but starting from very simple empirical models to mathematical models to data analytics, all are happening. So depending on your interest, you can pick what you want to try out and then you will do it. Some of the applications which we have developed include bus arrival prediction system. What you see as the picture there is actually a live system where you can go click on the route number, it will show the bus stop, you can click on the bus stop, it will show when the bus will come. So if there are multiple bus routes, it will show these are all the route numbers, which one you want, you can click and it will show. So there are many solutions that were developed. As I said, most of them are undergrad students' work. And I will stop with what are some of the challenging problems which are open, which if you get interested, you can work on. For example, dynamic scheduling. No city is doing that. They all have this fixed schedule, saying every 20 minutes one bus has to leave, or every 30 minutes one bus has to. Doesn't make sense. Peak hour you may need more, off peak hours you don't need. So how do you handle this in a dynamic way? Depending on the actual traffic situation, how will you schedule? Each of this problem, as I have listed, is an interesting open problem which can be worked on. Mobility as a service, for example, this Uber, Ola kind of system, which works completely different from a bus, completely different from a traditional taxi service. So how do we handle their scheduling, the routing, how do we do that? All those are, as I said, interesting problems. I don't know whether I will skip this as an undergrad student, may not be of interest to you. Basically, I was trying to tell what are all the challenges if you want to do this. One main challenge, as I said, is it's not traditional civil engineers topics anymore. You have to work with multiple domains, so it's very interdisciplinary in nature, and it's very difficult to transition, and that needs to be revision. Okay, so that's the last slide. As I said, we collaborate a lot in terms of bringing all these solutions. You can see civil engineering, computer science, chemical, electrical, engineering design, management studies. So various faculty members we work with. So as I said, it's something which if you wanted to be in a different department, here is a way you can still manage that. Okay.